All right. Before we start on the slide, let's just go over, or let's see, why don't y'all stop me before anyone has to go. That'll allow more people to come in, and that way I won't be repeating everything several times. So if anyone has to leave early, stop me at least a few minutes before you have to go so I can go over how we're going to wrap up the term. Okay? So, because I'm hoping some more will be coming in. So, anyway, I need to back off from this for a minute. I forgot something and get this one up there too, because there is a huge gap in the slides. So let's get started on this slide first. Okay. First, any questions on anything we've done so far? All right. Where we're beginning today is 18.4, and the title of this is an induced current. And let me just remind you so you can remind me. We don't have to do this one. We go from here to 18.7. We really only needed 18.1 and 2. I did too much last time. So let's move to 18.7. Sorry. That was fun though, wasn't it? Okay. Actually, these are very short sections, so it didn't take much to do that. Wow. 18.7 is less than a page. So let's go back to the other one. And let's see what they've got there. Okay. That's on this one. Okay, we do have a slide here. Now, this may actually be something that I don't know if you have to know it to know what you're going to be doing, but it might really be helpful to you. All right. All right. And this is talking specifically about scans, which is what y'all are going to be doing. Now, are y'all going to be doing mostly sonograms, or will you be other scan techniques as well? For instance, CT or MRI or other things. What's that? Okay, it's mostly ultrasound. Huh? I see. And that's all. You won't be doing, your position will open you up for other areas like that. Well, then this may be more of interest to you than practicality. Now, I don't know if you remember hearing me say from before that a moving charge induces an a magnetic field. Remember that? Moving charge creates a magnetic field. The charge going through the wire creates a field around the wire. Right-hand rule. Make a coil, it makes a stronger and stronger field. Okay? So a moving charge induces a magnetic field. Now, the reverse of this is true. A strong magnetic field can change the direction of a moving charge. And that's what they're illustrating here. If you had an electron beam, which perhaps could be sent from a source that you're using somebody is using in a diagnostic thing, send it through a magnetic field, and it bends the motion of the charge. Now, okay, I'll just leave it like that. I was going to talk about directions, but that probably isn't all that important. Here is the key that they use for this. If the magnetic field, say, is in that direction, the electron beam in this direction. Okay, now look at the field here. The field always goes from north to south, right? So the magnetic field is in this direction, north to south. The electron beam is coming that way, and then you cross the field strength with the beam, okay, and this is an electron beam, okay, which is a negative charge, so that would produce, if that was a positive charge, we would produce a force upward, and that's where it shows it's happening here, and that this doesn't seem to be upward to me. That actually seems to be going sideways. I'm trying to figure out how they got orientation, but again, it's a right-hand rule. So the magnetic field crosses the electron beam, and that gives you a force upward. So I guess that kind of can be, maybe if this were laying like this, that would be bending it upward. Okay. So that's how a lot of your imaging and other techniques work. Okay. Deflection of an electron beam by a magnetic field. And again, that comes from the fact that just like a moving charge induces a magnetic field changes the direction of a moving charge. Okay. That's the last slide in the chapter. So now we're ready for 19. Okay. And let's see, where do we begin in 19? Looks like we begin in 19.3. Okay. And actually what I'm going to do here is, I don't know why this does this. Okay. Well, come on and open. There we go. 19. Here. Okay. Here we go. Hit it. All right. We're going to start from this slide, even though that's not technically where we start. We start in 19, what did I say, 3? This will give you a little bit of background to build for 19.3. We do 19.3 and 19.5. So really we have very little to go with enough time to get it done, I think, fairly easily. So alternating current electricity. Now, what an alternating current does is, and really what we're talking about are the fields. The field is set up so the charges move this way, but then in a very short time they move back this way, and this way, and this way. So really, the charges don't do anything but this. They don't go flowing down the wire. They just go back and forth, back and forth, back and forth. Okay, we represent that on two-dimensionally as the current being positive, then 0, then negative, then 0, then positive, and 0. This is a sine curve, by the way. Okay? So the charge is flowing this way at A, this way at B, 0 at B, no charge at all, moving. This way at C, this one, okay, and then at D, it's back this way again. They left off the next 0 there, okay? So it's an alternating current. Now what does that? an alternating voltage, and that sends the charge back and forth and back and forth. Now, you might say, well, if the charge isn't moving through my light bulb or whatever else, how does it light it up? The energy that it has, that's what creates the light, the heat, or whatever, It's the energy, not just the moving charge. It's the energy held by that charge. And just because the voltage is alternating, that doesn't give it any less energy. In fact, it has pretty large voltages you can build up with alternating current, which you generally cannot with direct current. And if you did, it'd be sort of dangerous, I think. Now, they used to think alternating current was dangerous, and it has its dangers. Remember, we're electrical machines. Our eyes, our ears, our heart, our nervous system, everything's an electrical machine, okay? And if we get hit with alternating current, the currents in our body start going back and forth, and you can be dead pretty quickly, okay? So we don't want to mess around with either one of these, but actually in some senses, the alternating current does seem to be more dangerous, okay? Now, without going in too much detail, on a DC circuit, if you have the electricity, okay, we didn't do this in full detail. Here is the voltage, E, okay, and it's a constant. If you got a battery, whatever that battery is, 2.5 volts, whatever it happens to be. Here's the current that voltage is supporting, and that's a constant, okay? And what we didn't do, the power is the voltage times the current, so it's a constant, okay? Now, same thing holds for alternating current, except you're changing direction constantly. So therefore, your voltage is this blue again, okay? Up and down, positive, negative, very rapid at it too. And if the voltage is going that way, the current is going that way. So it goes up and down in phase with the voltage. Well, then the power is also operating in that manner. So you multiply this by this, you get peak here. Multiply 0 by 0, you get 0. 0 by 0, 0. You multiply negative by negative, you get positive. Okay? So your power is doing this kind of motion. Okay? Never negative. It goes up from 0 up and like this, so you have an average power here. Okay? Now, that's all we're going to talk about. You don't need to know any of that, but just to let you know, that's what's going on in alternating currents. Okay? Now, I don't think that was 19.2. All right. Later in 19.2 is this. It's changing voltage with transformers. And this is just sort of for background information for you. I bet you wherever you live, if you go outside and follow the wires from the building where you live back to the nearest power pole, you'll see there sort of a cylindrical looking contraption somewhere on that power pole. It's called a transformer. If a transformer ever goes out, you've lost power. Okay? And that's happened to us before. Okay? Now what that transformer is doing is stepping down the voltage. This is what it looks like. And it's happened many times over. At the generating plant, the power station, wherever that was that you got your power, that's producing a certain amount of electricity, voltage, current, power. Okay? And what happens there is they step it up like crazy, so it's very high voltage. And the reason for that, most of your line loss comes from the current, because the more the current, the more heat produced, more friction is going on. So if you can minimize the current, you can minimize line loss. Minimizing current means maximizing voltage. So that's why these big, tall power lines, you've seen them on these big steel towers, they usually cut out from under them, and stuff, and those are going across country, okay, or across the state, or across somewhere, long distances. They're way up in the air, so no one can get shocked by them, okay? And generally, a tree's not going to fall on them. They're so tall, they cut all the trees out from underneath them. You just don't expect to have those ever go down, because at such high voltage, that would be really deadly. In fact, some people are even afraid of the electromagnetic rays coming off of high voltage. I don't think there's valid concern there, but it could be. So what they do, before it leaves the generating station, they step up the voltage like crazy, minimizing the current, and send it across the wires. Okay, when some of those wires get into an area, say outside of Birmingham, they're going to start stepping down the voltage, because now you're getting around residential neighborhoods and stuff like that. So they step down the voltage, allowing the current to go up. Yeah, understanding for those short distances, they're going to have a little bit of line loss, but it's not going to be too bad because it's short distances. Remember, the length of the wire is also part of the resistance. Well, so they step it down some, bring it into the city, and I don't know if any of you are familiar with UAB campus, okay? Somewhere south of University, and over there, fairly close to the baseball field, there's almost an entire city block that has, they look like Venetian blinds in the chain link fence, so you can't see through it. Razor wire at the top. It looks like a high security prison. The thing is, it's to keep people out of there, not to keep anyone in there. And that is where they step down the voltage to go to the hospital and the classrooms and everywhere else. And they still may have others. So those are step-down transformers. That's what these are. Step-down transformer has a large number of coils on one side, the incoming, and a small number of coils coming out of here. And what that does, it steps down the voltage by the ratio of number of coils here to there. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. Here is 1, 2, 3, 4. Let's call it 8 to 4. So that would step it down by half, okay? That would cut the voltage. This is 500 volts coming in. It would be 250 going out, okay? That's what a step-down transformer does. That's what it's doing on that power pole outside your residence. It's stepping it down, so when it comes in your house, it's probably either 360 or 240, depending on how they wired it there, okay? And once they get it low enough, then you can run all your operations and stuff. But you have very short lines, so you don't mind that the current is a little higher. Well, that's what a transformer does. Now, some people call this a transformer too, and it is. But this is a different kind of transformer. This transforms alternating current to direct current. And any computer, cell phone, your cell phone chargers, you have a little, you'll see not one that big, but you'll see a little white box there. That's a transformer. That's a different kind from this because that's changing from AC to DC. Okay? Now, this has to be AC here. AC source, alternating current. Here's the reason. The current going through this wire has to be changing because only a changing current produces a magnetic field. So the changing current produces a magnetic field in this core, and then this one, the changing, and it's a changing magnetic field because this is always changing, the field's always changing. Because the field's changing, it induces a current in this one. But it's a lower voltage, higher current. Amperage current. Okay? So that's what's happening there. So that's different from that kind of transformer. Okay, this would be another step down. The magnetic field induced in the core by the primary current, the voltage induced in secondary core by the magnetic field in the core. That's what I just said. So just a repeat of that. Okay? Now, this would be a step-up transformer because you have fewer turns here, more turns there, so you're going to produce more higher voltage on the outside. This is what they have back at the generating plant, step-up transformers. This is what they have outside your house, a step-down transformer. You have more coils on this side than you do on that side. Okay. Now, are we in our section yet? No. This is the end of 19.2 right here. And this is sort of what I was saying. This represents the dam where the generating station. You're generating electricity there. It's hydroelectric. It could be a coal-fired power plant. It could be a nuclear power plant. It could be a gas turbine power plant. Whatever it is, you step up that to send it across long, long distances. And these are those big towers there. So it steps it up there, steps it up again. This is just a transfer station. Here is where it goes across those high voltage, very high voltage. The generating station's typically at 6,600 volts. By the time it gets here, 132,000 volts. So that's a step up of 200 times, I think it is. Okay? That's 200 times the number of primary coils as you do secondary coils. No, it's not, down the way. 200 times more secondary coils than you had primary coils because you're stepping up. Okay, when you get into the city, they don't all that big a voltage, so you step down transformers here and step down from 132 to 6,000, which is pretty close to where it started to begin with. And then it takes it to your house, and there's that transformer. Y'all seen them, haven't you? Okay? That transformer, before it goes into your house, steps down from 6,000 to usually it's going to be either, they say 110, 220, it could be 330. And then they split that. Your high heat producing appliances need the 220. Generally your air conditioner needs that. Your clothes dryer needs that. Your oven needs that, or range hot, whatever. Your hot water heater needs that. Anything that produces a lot of heat. In fact, look at the plugs. If that plug has a big 3-prong and one of them has an L or something like that at the top, you know what I'm talking about. That's 220. Okay? The regular ones that plug in here, that's 110 or 120. So they sometimes call this 120 and 240. That's what I called it to begin with. They're calling it 110 and 220. The difference is, by the time you actually use it, it's usually lost a little bit of voltage and gets down to around 110. So that's what we use. Regular plugs like this, those are 110, and the big plugs, those are 220. All right. That's just the background. And that's the last slide in the whole chapter. My word, this is such a lot. I'm sorry. Okay. No, that doesn't mean we're through. Okay. That means we're through with this slideshow, though. Okay. Yes? I'm sorry, I can't hear you. Okay, you're going to need to leave soon? Okay. All right, here's how we're going to wrap up, and then we'll get into inductance, which is what we really don't cover today. All right, today, Tuesday, next to the last day of class, okay, we're going to do as much as we can get in chapter 19, and then on Thursday, when you come to class, And this is why I wish some people were here that are not here. I'm going to be returning all of your tests to you. I would have returned them sooner, but there's at least one person who hasn't turned in every one of the tests. And some of the tests, it's way more than one. Okay? Now, there are some I haven't graded yet, but there's nobody who's turned them in. If they had turned them in, I would have gotten those graded so I could get rid of them, get them back in your hands. So the first thing I'm going to do on Thursday is return all of your papers to you. Okay? And then we'll continue with Chapter 19, whatever we've got to go in Chapter 19. I'll also pass out to you your last test. It's not going to be a comprehensive final exam. It's just final meaning last test. And that will be from chapters 18 and 19. Okay? What we haven't been tested on yet. And that I'll give to you. And at the end of the class, when I give it to you, I'll tell you which questions you should be able to answer and which you will not. Okay? And that's what we're going now that I look at this is the test I used last term. When you asked for it, that's all I had available. And actually this has questions on it based on some of the stuff we just sort of skipped over. So I think I'm going to go back and pick up alternating current. Let's see if anything else is in here. Okay. I think we covered all the rest of it. So I think I'm going to go back and, now that I look at this, and but we went through all the slides, didn't we? They were pathetic. Okay. Yeah. But we'll start over because some of these questions are based on, see, last time I did more of Chapter 19. When I went back and reviewed, I said, I'm not sure they need that because we didn't get to finish last time either. And this time we're well on the way to finishing, but we got plenty of time to do so. So I want to make sure I hit all the questions that are on here. So, yeah. So we'll go back to the beginning of 19.1, even though there were slides on it, they really didn't say a lot. So I think what I'll do is go back and do that. And then I think we'll hit all these questions between today and tomorrow. Okay, so that changes a little bit of my game plan now. Okay, so we'll do that. I'll give you your test. I'll let you know if we didn't get to cover all those, any questions you can skip. Okay? And then I'll give you your test. And then next week, if you need to see me, if you want to catch me on the Bessemer campus, on Monday, Monday is a class day. This Thursday's the last day of class for Tuesday, Thursday classes, but Monday's the last day of class for Monday, Wednesday classes. So my Monday, Wednesday classes will be meeting on Monday. I teach from 8 in the morning until 9:40. I have a little 20-minute break, and then from 11 to 1:40. After 1:40, I'm through teaching. So usually I'm still up in the classroom, doing things on the computer and stuff, getting attendance, that kind of stuff done. But then I head down to my office, usually somewhere around 2. So from 2 to 6, I'm usually in my office. Okay? So if you did need to see me on Monday, the best time would be 2 to 6 on the Bessemer campus. Now, if that's not convenient to you, which I'm guessing it's probably not, I know Sydney's been over there because she had a class under me there last spring. So I know she knows where I live over there, but you probably don't.
What room number are you?
It's in the A building, room 265. Are you familiar with it?
I'm familiar with the Bessemer campus. I figured out.
Okay. Are you at all familiar with the Bessemer campus? Oh, you are? Okay. You know,
room 240 what?
265. Do you know where the orientation classroom is there? No, you don't know that. Okay.
I find it.
Okay. The A building, the numbering is outrageous. It almost makes no sense whatsoever, but it does make a little sense if you really stretch your imagination. But you can wander around that building and not know where you are. Okay. It's a big, sprawling building. So, yeah, I like your word. You know that you're confident. Okay, so I'm there available from 2 to 6 on Monday afternoon. Then Tuesday, I'll be there 7:45 in the morning up until noon. I don't have any. Normally have classes, but that's final exams, and those 2 classes in the morning have take-home finals like you do, so they are coming in anytime they want to come turn them in. But at 12 o'clock, that class has an in-class final, so we're going to be. I'm just estimating I'll be in the classroom, and that classroom is 255. So if you need to see me actually either Monday or Tuesday, my classroom is 255, my office is 265. So I'll be in the classroom giving the final from about 12 to 2. I doubt if it'll take them 2 hours to do it, but that's my best guess now. Okay. Then I'm back in the office from 2 to 3:30. At 3:30, I'll leave Bessemer to come over here. So I'll be here from 4 to 6, both Tuesday and Thursday evenings. Okay? Y'all aren't required to be here, but that's when I will be here because that's, and I'll be grading papers and working like crazy. Now, if it's really hot here, I may go to a cooler room, but I'll tell the ladies in the office where I'll be. Okay? So I'll be here 4 to 6 on Tuesday and Thursday. Okay, then on Wednesday, I'm back on Bessemer again, and no more finals, except things that people are turning in, take-home finals. So I'll be in my office basically from 7:45 in the morning till 6 o'clock in the evening, all day long, somewhere near 265. I won't be in the office all the time, but somewhere close to that, to 7:45 until 6. Then on Thursday, no finals then either, except people bringing stuff in. I'll be in the office from 7:45 until 3:30. 3:30, I'll leave to come over here, and I'll be here 4 to 6. Okay?
But there's no class on next Thursday.
There's no class on Thursday, but I'm giving y'all a chance. If you can't get it into me on Tuesday, I'll be over here on Thursday. Okay? And I'll be grading like crazy. And if I've finished all my grading, I'll be entering grades or do Blackboard or something. And if I got all that done, I'll be working on emails because I'm way behind on emails. So I've got plenty to do. I'll be over here doing it. Not gonna work. Okay. Now, that leads us up to Friday. Now, I'm not really sure. In fact, I can go check. But you see, June and July, the school was closed on Fridays. But you see, that Friday of finals week is actually in August. That's August 3rd. And I don't know if we're open or not. I think we're not, but if you hold on just a minute, I'll check next door and see if they know for sure. It's as I thought. The college is not open even though that's in August, the college is closed August 3rd, which is kind of good because I'm not going to be on campus anyway. I've got a treatment that day, and I've got to be in the labs by 7. Treatment starts sometime after 8, and I'll be there all day. And even when I'm through, I go home and go to bed because the Benadryl just knocks me out. So anyway, you can't do it. I was going to say if the college is open, you could slide it under my door, office door, 265, but you can't. College is closed. So get it to me Tuesday through Thursday. Okay? Tuesday, Wednesday, or Thursday. Tuesday or Thursday, here's 4 to 6. All the other times on Tuesday, Wednesday, and Thursday, best one counts. Okay? Now, grades are due, we have to have them in by noon on Monday. The next Monday, which is what, the 6th, 5th, or 6th, something like that. 6th, I think it is. Okay? So, and by the way, I don't know if you've been around Lawson long enough, on that day when grades are being entered, you cannot access Student Suite at all. And it's kind of crazy, but true. The system only has something like 16 ports. And typically at the end of a term, all the students in the world are trying to check their grades. So everybody's on Student Suite. Only 16 people can be on at a time, and if 16 students are on, not a single faculty member can get on to enter grades. But the students are looking for the grades, so they stay on it, and it's a circle that doesn't end. So what they found out, once they discovered that's not going to work, they shut down Student Suite on the day that we're entering grades, so the faculty have a chance to get to one of the ports to enter grades. Now, if you want to know what your grade is, go to Blackboard. Because I do the grades on Blackboard before I put them on the suite. So you'll see sooner looking at Blackboard. So on that Monday, don't ever try to do any Student Suite. Go to Blackboard, and hopefully you'll see your grades there. If not, wait a few minutes, hours, or whatever, and try again. Before noon, the grades will be there, I guarantee you. Again, okay. So that's how we're going in. And as far as I know, there's no student course evaluations this summer. Have y'all seen any word on any? An email? I haven't either. So, of course, I miss emails sometimes. So, all right. So that's where we end there. All right.
Do you give extra points if we do the survey?
Say that one more time.
Do you give extra points if we do the survey?
If we do what?
The survey, the end of course survey.
Yeah, but there aren't any surveys. That's the thing. Oh, there are some. Well, that's what I thought I just asked you.
They send it on our personal email as opposed to the school.
Oh, really?
I got one last week.
Last week. See, I've been asking students just about every class, but when they kept saying no, 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 I quit asking. So, because usually they open them up like 2 or 3 weeks before the end, but they just opened it last week. Okay. No, I don't have any mechanism for doing that. I didn't put it in the syllabus. So, but I really appreciate it if you do. I never get to know what you did. I can check to see if you did it, but I never get to see, and I don't want to see what individual students said. All I see is the average. And there's no way to tell what any student did. So please do the student course evaluation. I did not know. I'll have to tell all my classes. So they do have it out there. That is good to know. Huh? Okay. So let's go back to, okay, we did that slide, we did that slide. All right. Let's hit, and here I'll go to this one, and we'll go from current slide. All right. Now, here are the things you need to know with alternating current. Now, before in direct current, we called current capital I, right? In alternating current, since that is never the same, it's never changing, it's not a constant, it's changing, they call current little I. Let me get my pen back. Okay. So the current is little I, and that's equal to what they call I max, and that's not a big theater, okay, times the sine of theta. Now, what in the world is theta? And by the way, this is called the instantaneous current, okay? Little I is the instantaneous current at any instant. I max is the maximum instantaneous current. If you go back to, remember how those graphs look? When they do this kind of notion, this is I max, the maximum current it'll ever have. Okay? That's your I max. The instantaneous current is the current at any time here, okay? And theta is the angle measured from the beginning of the cycle. Now that doesn't say a lot, does it? I wish they had figure 19.4 on the slide set. They don't. It just shows as the angle is going up. When it starts at 0, your current is 0. When it starts going up, the current is going up. When it reaches 90 degrees, you're at the top. When you go around and start down the back side, it's still positive, but now decreasing. When it reaches 180 degrees, it's 0 again. But now when it keeps turning, now it goes negative, and that's represented by this. Now this is not a very pretty looking sine curve. That would be a little bit better. But that would be when it's down here, and when it reaches 270, it's at -1, okay? The sine is. That's your maximum current, only negative now. Go back up, and it's the same thing as here, and then everything repeats itself. That's what a sine wave does, okay? So theta is the angle measured from the beginning of the cycle, okay? Now, that's your current. Here's the instantaneous voltage, because voltage does the same thing. This is your Emax, okay? That's the maximum voltage that can be produced by your device. And that's Emax times the sine of theta. And theta is the same as before, okay? Maximum voltage. So let's do example 1, okay? All right. The maximum voltage in an alternating current is 75 volts. So what do we call that? Maximum voltage. What was the symbol for that? It was just up there. Emax, okay? That's your maximum voltage at 75 volts. Is that a 0.0? No, just 75 volts. Find the instantaneous voltage when your angle is 35 degrees. So the instantaneous voltage is what symbol? No, little e. Little e. And what is little e's formula? E max times the sine of theta. Okay? Well, your theta, by the way, that was your 35 degrees. Theta is equal to 35 degrees. Okay? So now we just plug and chug. So that'd be 75 volts. Now, does anyone know how you do a sine theta? I almost need to see your calculator. Do you have them available? No. You have one. Okay. Is yours? Okay. Yes. Okay. You just pulled up a cosine and there it is. Okay. Now, can I clear this? Okay. Clear all. Okay. Now, how we would enter that. Now, this is this calculator. You may have one that you enter it differently. If you have any questions, I'll try to help you figure it out. This one that I have here, I would enter 7, 5. Now, you could put times if you want to, but I believe it takes care of it if you just put sine of 35. Oh, back off. Okay? What we need to do first is do, on this calculator, it's the second angle. And the second angle, it happens to be on number 1, which is degrees. That's what we've got, degrees, you're right. So I'll enter that, whoa, but back off now, 35 degrees, okay? I'm going to close parentheses, I don't think you have to, and press enter, okay? And this tells me 43 volts. Is that what they got in the book? Okay. Did everybody see that? Okay. Now, did anyone on your calculator not able to get that? You just type it in just as it is. 75 sine 35. If you're in degree mode. Now, if you get some wacko answer, let me check and see if you're in the right mode. Because your mode there, or your angle thing, you have either degrees, minutes, seconds. I can't read the next one. Oh, the R is radian, and the G is gradient. And then you're back at the top again, DMS. I don't know what that stands for. Okay? So you want to be in degree mode, and you're fine. Okay? I'll delete that. Okay. If anyone not be able to get that, do it on your calculator. Okay. All right. 75 sine, and see, open parentheses. Oh, let's check your mode. See, here's yours, DRG. That's degree, radian, grade. Okay. Oh, wait, you're in degree mode. So you see, you hit that, you're in degree mode. So you're fine. Sine 35, close parentheses, 43. Okay? Everybody see it? The reason I say that, some of the older scientific calculators, you actually have to enter the angle first and then the sine function. And that's why I wanted you to make sure your calculator worked. Okay? So, now, and then we have the curves here, and they talk about being in phase and out of phase with voltage and current. And that's a bit bizarre for them to be out of phase, but it can happen. Okay? Now, there is another value that's of importance to us, and that's the effective value. Okay? And here's where that comes from. Remember in direct current, we talked about current being in, oh, by the way, the same formula works for current. So if you're doing little I is equal to I max times the sine of theta, same way. Whatever your I max is, put it in. Usually it's the same theta. Okay? Now, when you're trying just to do things like Ohm's law and things like this, that you don't want the instantaneous current, you just want kind of the average current, okay? The effective value of that current. Here's what the effective value is. I is equal to 0.707 times I max. If you just want an average kind, it's not really an average, but it's called the effective current, that's what you use. Or, if you want to know what I max is, and you know what the effective current is, that's 1.41 times I. Okay? So if you want to know where I is the effective value of the current, and I max is the maximum instantaneous. And by the way, same formulas work for E. The effective voltage is equal to 0.707 times E max, and E max is equal to 1.41 times E, your effective voltage. That's on the next page. Now, do you have any idea where that comes from? Let me tell you. If some of you have you got the calculators out, do you see your square root key? Now, I don't know how your calculator works. You either press square root key and put 2 under, 2, or do 2 and then do the square root. I don't know how your calculator works. But do that, and what number do you get? Square root of 2. 1.414. Okay? Now, hit your 1 over x key, x to the minus 1 key. And what do you get? 0.707. That's what you're dealing with. You're either dividing by square root of 2 or multiplying by square root of 2. So if you don't want to remember the formula, all you have to do is this is dividing by square root of 2, that's multiplying by square root of 2. So if that's easier for you to punch than 1.41441 or 0.707, you can use that. That's exactly what it's doing. All right, so let's do example 2 at the top of the next page. And let's erase that ink so we can do this one. The current supplied to a woodworking shop is rated at 10 amps. Now, let me just tell you, it says is rated at. That means that's your effective current. That's your I. Not I max, I, effective current. What is the maximum value of the current supplied? Remember how to do that? I max, that's what we're looking for now, is equal to what? 1.41, right? Times I, which is 1.41 times 10. That's easy. And that's going to be 14.1. They probably don't put the, they put the, because it's 10.0. 3 significant digits. Okay, here's something to remember. When you see the max, that means that's the highest. So if you see the I, it doesn't have the max, that's the lower. So if you come up with an I max that's less than the I, you did it backwards. If you come up with an I that's greater than I max, you did it backwards. Okay? The I is always less than the I max, and the I max is always greater than the I. That's why you multiply the I by 1.41, and that's why you multiply the I max by 0.707. Okay. Does that make sense? Okay. And that, by the way, is in amps. Current is always in amps, because that was in amps. All right. Homework exercises here would be any of the odds 1 through 27. They gave 2 examples and give you 27 problems. That's plenty to work on, isn't it? All right, let's move then to AC power. And we did have a slide that was like that, and we'll come back to that in a minute. Let me give you the formulas first. Okay? So let's do the formulas. When the load has only resistance. Now here's the key, folks. The load is only resistance. Now, when we were doing DC, that's the only resistance we had. That's the only load we had was a resistance. So now, when you're on AC power, when the load has only resistance, the power in the AC circuits is found the same way as you did in DC circuits. Now, we didn't do this before, but I showed it to you before, and let me give you that basic formula. Power is equal to voltage times current. That was true for DC. It's true for AC. But here we use that effective, or whatever they just called it, one we just did. Effective voltage and effective current. That's why they use V and I. Same as the other. Now, do y'all remember Ohm's law? Please say yes. Okay, what was Ohm's law? I equal V over R. That's one of them. Give me another form. V equal IR. And the last one, R equal V over I. Now, we're only going to need the first 2, but I just wanted you to remember those. So let's see what happens if we put, instead of V, we put IR. Well, then we have power is equal to IR times I, which basically is I squared R. So that's why I said, I think I said it, when you have a lot of current, you're using a lot of power. Remember the things that draw a lot of current? Those things that produce or deal with heat. Your air conditioner, your oven, your clothes dryer, your hot water heater, anything that deals with heat. Even your iron. It's not as bad as the others, but it still is. Your hair dryer, okay? Heat. So that's going to do a lot of power, because the larger the current, and the more heat comes from the current, the larger the current, the more power you're using. Okay? So V is equal to IR, or P is equal to VI. That's 1. Okay? But now let's do the other. P is equal to V, and instead of I, we put IR. No, I'm sorry, we just did that. We put V over R. The I is equal to V over R, so that gives you V squared over R. So again, your power, as your voltage goes up, it also goes up by a square, but now you're dividing by the resistance. In the current, you're multiplying by resistance. So the power is more susceptible to a high current than it is usually to a high voltage. Because quite often your resistances can be quite high, and that drops it down some. Okay? So those are the three formulas you'll see on page 19, on page 528 under 19.2. The three formulas for power. Okay? Now, example 1 then deals with that, so I'm going to delete these, and we will do 19.1. What power? So we're looking for power. That's the unknown here. That's what we're looking for. What power is used in a resistance of 37.0 ohms? So that's your R resistance, 37.0 ohms. Okay? If it has a current of, and current is what symbol? I is equal to 0.48 amps. 480 amps. Okay? Flowing through it. So what power formula deals with resistance and current? One we just put on the board. Second? I squared R. Exactly. I squared R. So this will be 0.480 amps squared times 37.0 ohms, and that will give you how much power usage? .48 squared times 37. So you're going to be pretty low. Say again? 8.52? Exactly. 8.52. Does anyone remember the unit for power? What? Watt. Yeah, exactly. Okay. Watts. Okay. Now, remember back when we were doing the other forms of energy and power, you could do horsepower, you could do all these other things. Guess what? By the time electricity came along, the SI system was in play, so everybody decided to use watts. Okay? So when talking about electricity, even in the U.S., we use watts. Okay? Voltage, current, and amperage and watts. Okay? We don't use anything different like we do in everything else. So let's do example 2. Again, the question is power. What power, we don't know, is used in a load of 12 ohms, so that's going to be a resistance of 12.0 ohms, if the voltage drop across it is 110 volts. So your V here, I like to call it delta V, but this book doesn't, so I'll leave it like this, 110 volts. And they put a bar over the 0, meaning it is significant. So what's your power when you're dealing only with voltage and resistance? V squared over R. So that would be 110 volts squared, but divided by 12.0 ohms. Okay? Punch that in your calculator and see what you get. Somewhere around 100, no, 1,000, yeah. That's right. Second? Okay.
1008.33.
Point something? Okay. Now, how many significant digits do you have here? 3. Here? 3. Oops, that was the previous problem. Sorry. Here? 3. There? 3. So we only need 3. So count. 1, 2, 3. Look to the right. The 8 is more than 5, so you make it 1, 0, 1. And then you just put a placeholder 0 there. No bar over that. And that would be watts. Again, power is measured in watts. Now, that's a big number, 1,010 watts. What if I wanted to use a smaller number but a bigger unit? What would I use? You do a power of 3. That would be smaller number, 1.01. Okay, 10 to the third. And what is 10 to the third, or 1,000? What metric prefix? Kilowatts. Okay, we don't know what kilos are, do we? Never mind. Okay. So that's 1.01 kilowatts. That way you don't have the extra 0 you don't know what to do with. Move the decimal and you got 1.01 kilowatts. Okay? Now, the next little section here is called Transformers and Power. And they have a highlighted word that I usually like to say, but I'm not sure you really need to know it. It says the uses of direct current in industry are somewhat limited. Primary applications are in charging storage batteries, electroplating, generating alternating current, electrolysis, electromagnets, automobiles, ignition systems, computers, cell phones. I mean, there's a lot of them, really. However, AC can be changed to DC by a device that's called sometimes a transformer. It's a rectifier. This is not really a transformer, so I bet if I looked at this, it will say AC adapter. The better word would be rectifier. Okay, that's what that is called, a rectifier. Okay, so just throwing that word out. Now, as I said before, your heat loss, or the power that you've lost, and heat is energy, and power is energy per time. So when they say the heat loss, or the P, that's per unit time, per second, is P equal I squared R. This one right here. Or, if you know the other one, I didn't write it down, did I? I just listened to you. E squared over R. Okay? So either one of these give you your power loss, or your energy, you might say, wasted. Okay? And because the I squared, that current squared, that is going to be your biggest power loss, we want to always minimize that loss. So here's what example 3 is talking about, and here is where I'll delete this so we'll have more room to work. A plant generates 50 kilowatts. That's 50,000 watts. Kilo means 1,000. 50 kilowatts would be 50,000. But because it was 50.0 kilowatts, that means that 0 is significant. That means that one is, the other two are not. So this is your power in watts or kilowatts. Either one. Same thing. Okay? Of power to be sent to a substation on a line with a resistance of 3 ohms. Now that's pretty small, but it can be significant. So the resistance is 3.00 ohms. Okay. We know that some power will be lost as heat during that transmission. That power loss is, and they give it in terms of current. Okay? That the power loss is I squared R. P is equal to I squared R. I can't stand sitting too long. Drive my wife crazy. I have to get up and move around so I just get stiff. That's what you get from being old, you know. This chair is a comfortable chair, but I've been in better ones. Okay. And I'm sitting weirdly too, because I have to sit right at this corner because of everything here. Okay. Sorry. So, the A question here is, how much power is lost if the transmission is at 1150 volts? So what is a power loss? That's what we're looking for if the transmission is at E is equal to 1150 volts. Okay? Ooh. Now, all right. What we've got to do first, and they're taking you around this a strange way, but it's perfectly fine. Remember one of our other formulas for power. If all you dealt with was current and voltage, what was that one? P is equal to? Second? EI, exactly. Thought you were going to say O, EI, EIO. Never mind. Okay. So the power is equal to EI. This formula right here needs I. They gave us V, but we already knew P, so we can get I, can't we? So how can we get I out of this formula here? Yeah, do you say I is equal to P over E? Is that what you said?
I didn't think I just got to the I.
Yeah. Okay. You see, if you divide both sides by E, that's what you get, right? So then let's put our power in. That was 50,000 watts, okay, divided by your E of 1150 volts. You need to get the watts to use volts and stuff, so, and current and amps. So if someone will tell me what that gives you on your handy-dandy little calculators. 43.47. Okay, and that will be measured in amps. Okay, so let's take that and plug it in here. So your power loss is going to be, you can leave it in your calculator just like it is, 43.47 amps squared times your resistance of 3.00 ohms. And what do you get? You left it in your calculator just like you had it, square it, and then multiply it by 3. Anyone get it? 5,000? Okay. Say again? 5? 5, 6. 6, 8. Okay. Now, we don't need that many digits. We only had 3 here, 3 here, 3 here. So let's go 1, 2, 3 digits. Look to the right. Greater than 5. So let's call that 5,670 watts. Whoa, that's a big number. Okay, now they rounded more than we did. Shame on them. Let's make sure. Yeah, they rounded to 43.5. I don't like to round till your final answer. Okay. So anyway, that answer, the A part, was 5,670. They said 5,680. So they were a little off. Okay, but not bad. Okay, B. What percentage of the power generated is lost in transmission at 1150 volts? So let's see. Percentage, by the way, a percentage loss is, I think, what they're calling that. Yeah, percent loss is the amount lost divided by the original amount. Okay, and then make that multiply by 100 to make it a thing. So the amount lost was 5,000. If you have that number in there, don't round it, leave it in there. 5,670 or whatever it was, 668, whatever it was in there, okay, divided by the original, which is 50,000, okay, and what do you get when you divide that? 0.1133, okay, and that would be, that's your decimal amount. Your percent would be 11.3. I only need 3 digits. Look to the right. It's less than 5, so leave it alone. 11.3%. That's a lot of line loss. Now, they said 11.4 because they used a bigger number than we did. Okay? Now, what if we did the transmission was at 11,500 volts, so we stepped it up by 10. So this time, this is the B part. The C part is going to be, what if your voltage was 11,000, what was it, 500? Yeah, okay. So this time we're going to do E is equal to 11,500 volts. And neither 0 is significant, just the 115, okay? Just like before. Again, we do everything just like we did before. Find out what I is. I is equal to P, which is 50,000, divided by, and that's volts, divided by, watts. No. Yeah, watts. Divided by E, which is now 11,500. So what's your current? That's volts. The current now is going to be 4.35, right? I'm going to keep the 4.7 for now, and that would be amps. So you dropped your current a lot. Now we're going to calculate the power loss, PL, just like we did before. It's I squared, which is 4.347 amps, or whatever you have in your calculator, squared, times, again, your 3.00 ohms. Not going to be a very big number, is it? About 50-something? Second? 56.7971. So I count 3 digits, look to the right, that's a 1, so we'll ignore that. So 56.7 watts. Whoa! Last time the power loss was 5,070 watts. Now it's just 56. Now, okay, let's see if they got 568 just like they did before. Wait, yeah. Now, what to get the percentage, that's the D part, what percentage of the power generated is lost in transmission. So your percent loss, this is D, again, percent lost is equal to total loss, what did I call it before, amount loss, okay, it doesn't matter, total loss divided by the original amount, okay, and that would be 56.71 if you wanted to carry that, whatever you want to do, watts divided by your 50,000, and see what you get then. A pretty small number. 0.0011 or something like that. Is that right? 0.001133? 342, okay. Well, you only need, you count 3 digits, look to the right, 4 is still less than 5. So that would be, your percent would then be 0.113%. Whoa, I think I can live with that one. 0.1, I mean, just barely over 10%. I mean, 1/10 of a percent. That's pretty good. Now they did 4, we did 3. Okay. Now, there's one more question. Compare the power losses at the two different transmission voltages. It shows that the higher the voltage, the lower the current, and by far the less percentage power loss. Huge difference. Right? Now, I've already given you some of the rest of this. How are we doing? Woo! Okay. Let's, how in the world do we do that? How in the world do we bring our voltage up so that we can drive our current down, that we can save the power loss? Okay? That's changing voltage with transformers. Okay? Now let's see. I think I'll clear this slide. Are y'all okay with that? I'll write down what they're mentioning here. We've already talked about a transformer. That's not these strange looking things that they make movies out of. That's what your kids use. That's not really a transformer. What it is doing, that's transforming from one machine to another machine to another machine. Well, what this is doing is transforming voltage and current. Okay, so in some ways it's like that. Okay, consists of 2 coils of wire wrapped around an iron core, shown in the figure. And maybe I should bring that up. So let me do that. All right. Now, we sort of zoomed right on past this slide. We'd already talked about it before. That's your average power, P average. And again, capital P was with DC, small I and small p and small e are your instantaneous, but then they keep the average power as a small p here too. Don't know why, but they do. Okay, there's your transformer. Okay, it's transforming an incoming voltage to an outcoming voltage. Okay, so I'm going to give you the names I use for that. I'm going to get my pen back to black if it'll let me. It won't let me. There we go. All right. We call this over here the AC power source. Whatever the voltage coming in is VP. The P stands for primary. That's the input side. So I'm going to put input here. Okay? The primary side. Okay? You have the number of coils on the primary side, and that would be N sub P. The number of coils on the primary. Okay? Then you have the number of coils on the secondary side, in other words, the step-down side, on this case it would be, and that would be number of coils here. They usually call them turns. And then what you get here is the VS, the voltage on the secondary side. That's the output voltage. Okay? I like to remind myself of that. Here is the formula you use with those devices. The voltage on the primary side, the ratio of that to the voltage on the secondary side is the same as the ratio of the number of coils on the primary side to the number of coils on the secondary side. Okay? That's a direct proportion. The higher the voltage, the higher the number of coils. The lower the number of coils, the lower the voltage. Okay? Now, do we have time to do a quick example 4? Okay, you didn't have to leave early today, huh? Okay. So we want to start with the example 4 next time? Okay, I thought for sure I got me a pencil out, but maybe I forgot to. Does anyone see a pencil up here? I must have forgotten that. Yeah, I always forget something. I don't know why. The old gray cells ain't what they used to be. Yeah, there's my, no. I must have gotten my pencil out. Is that mine?
She give you
No. I know I have one.
you have that one.
No, there it is. I knew I did. I just couldn't see it. Okay, we'll start next time with example 4. Okay?
Now, before you close that out, I have 2 questions.
Okay.
On chapter 17 page.
Okay?
Number 4 and number 10.
Okay, let me get back over here. And, let me sit down softly. All right, good, thank you.
Monday or Tuesday, drop off their textbook before classes.
Okay,
I won't be here Thursday.
right, you won't be here Thursday, and you said,
But I'm going to drop this to this off either Monday or Tuesday.
Monday I'll be over there.
I wrote it down.
Okay, Tuesday I'll be there and then here. Okay, you're going to go over there.
I'm going to come to Bell's.
Okay, welcome to Bessemer. Okay. Okay. Now, here's something, since Deidre's gone, I didn't want to make a special deal about it, but since she's not going to be here and I gave hers early, I don't mind giving y'all's early too if you want it. Okay. Now, understand, we haven't done all this stuff yet, so some of it's going to be mystery meetings, so don't get panicked, but you should be able to do the first part of it. Okay. Parts of the first part. Okay. Oh, even swap. Okay. Oh, you did. All right. And I don't know if I told you this before. I think I've whined about it before, but I don't know if you realize. Up until this afternoon around 2:30, for the last week and a half or maybe 2 weeks, I've been doing almost nothing but trying to get ready for our planning hearings. That happened today while I was teaching and stuff, so I couldn't be it. But I was on campus last night until after 9:15, getting ready for the meeting that I could go to, of course, getting all the data prepared and that kind of stuff. So I'm way behind on grading. But from now on, grading city. I know that a student has a question. He said he was going to come by tomorrow during office hours. Hopefully it won't take too long. But that's all I'm going to do from now on is grade, and try to whittle down the stack. Okay. So you're talking about which test?
17.
Okay.
I bring like a different example there.
Okay. What is the questions again?
Okay, so like on number 4 on the test.
What is number 4 on the test? I'm not sure.
What I did was I pulled up, like this is an example similar to number 4 on the test. So
Okay, is this number 4 on the test? Is that it, or a different test?
Yes.
Okay,
Yes.
I didn't know which test you were talking about. Okay.
So
All
I would
right.
say, like, if you just show me how to work this example,
Okay.
that way it won't be the one on the test.
Right, exactly. Okay, I don't want to do that. What I want to do is this. Oh, okay. Discard that, and I'm going to close that out and pull up this one and get my pen back. Okay. And again, I don't mind doing this so everybody can see. That's what I'm doing. So if you'll, okay. What was the page number and stuff like that?
It's on 464.
464. And which number?
Number 3.
Okay. So this is page 464. This is problem 17.5. And which one? 4?
3.
3. Okay, 3. Number 3. All right.
Or 4, either one.
Find the resistance per foot of number 22 copper wire if 580 feet has a resistance of 9.57 ohms. Okay? Now, all right. What we're looking for, it says find the resistance per foot. So that's going to be resistance divided by length.
Okay.
That's what we're looking for.
Okay.
And then they proceed to give you the resistance, okay, which is 0.651 ohms in, is it 500 feet?
580 feet.
Oh, I'm sorry. I'm looking at the wrong one. Sorry.
Oh, he's looking at
No, I'm sorry. I'm wrong. Okay, let me go back. Okay, 3. I'm sorry. Okay. Find the resistance per foot if 580 feet, that's in the denominator, that's the length, 580 feet has a resistance of 9.57 ohms. That's all there is that they're looking for, I think.
Yeah, I did
Let's
that.
check.
I kept that. I'm like, this number is too big.
Okay. Well, it was the answer in the back?
On number 3.
Yeah. It's going to be a small number. Really small number. Do 9.57 divided by 580. I could do one on my computer, but then I'd have to. 9.57 divided by 580. It's going to be a pretty. 0.165. 0. What? 165. I thought that was too big a number. And that would be ohms per foot. Is that the answer in the back? That's it.
Yeah. Like that one on the test, I did like that, but I was like, I think that's wrong. Okay, last one, number 10.
Number 10.
Let's see if I can find out. I know it's one in there.
Oh, it's not number 10 on this. Okay.
It's 10 on the test, but I'm trying to say, I know it's like a different
Okay.
example in the chapter.
10 on the test is 3 charges, blah, 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 blah. Okay. It seems like this should have been early in the chapter.
Here's one on 17.3.
17.3.
It's on page 457.
457. I was thinking it should be earlier in the chapter. 457. Got it.
And it's number 7.
Number 7. Okay. So let me just go to a clean page, okay?
Okay.
All right. All right. Page 457. And this will be problems
Problem number
17.3. And number which?
Number 7 or 8, both of them.
Okay. I think the odd answers are in the back, aren't they? Oh, they are. Yeah, so we'll do 7. 3 charges are located along the x-axis. Charge A, which is plus 3 microcoulombs, is located at the origin. Okay, I'll just be very generous here. Here is A at the origin, and 7. 3. I'm going to call it Q for A. That stands for charge. Is 3.00 microcoulombs. Okay? Charge B is located at 0.4 meters. Okay? And charge 5 is at 0.75 meters. So we'll say 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. Okay. So at 0.4, 1, 2, 3, 4. So here is B. And charge B is 5.5 microcoulombs. So Q sub B is 5.50 microcoulombs. Okay? And this is 0.400. Yeah. Okay, that's what that is. This is 0.100 meters, 0.200 meters, and so on. So, charge C is a negative charge, okay? And this is at 7.50. That's 4, 5, 6, 7, so 7.5. So that's 0.700 meters. This is 0.750 meters. This is 0.0800 meters, just to give you an idea. Okay? Now, the charge there is negative. This is point C. So Q sub C is equal to negative 4.60. I can't even read my own writing there. It's supposed to be a C, and it doesn't look like a C. Q sub C is equal to negative 4.60 microcoulombs. Okay. The A part of this question says find the total force and direction on charge B. Okay, so we're looking at charge B here. Total force and direction from B. Now first, just taking a look at that, both A and B are positive charges, so which way do you think B is going to be wanting to go from A? Like charges? Yeah, to the right. They're repelling. But C is a negative charge, so it wants to go to the right. So we're going to be adding the forces because they're both going to the right. Okay? Now, it's Coulomb's law is F is equal, that's force, is equal to K Q1 Q2 over R squared. Okay. Now the Q's have to be in coulombs. Okay. So your K is 9.00 times 10 to the 9th, and that's in Newton meter squared per coulomb squared. Okay, not squared, not coulomb degrees. Okay, times Q1. Well, your Q1 here is your QA, so let's make that QA and this QB. I should have done little q's. I forgot to use that. Okay, your Q here is 3.00 times 10 to the minus 6. Microcoulombs mean 10 to the minus 6 coulombs. Times QB is going to be 5.50 times 10 to the minus 6 coulombs. And then we're going to divide that by 400 meters squared. Okay. It's a 4. I can't read my own writing. Yeah. 0.400 meters, but you got to square that. Okay? Okay. Now, and notice this coulomb times coulomb is going to wipe out the coulomb squared, and meter squared is going to wipe out meter squared. So you're going to come up with newtons, which will be. But remember, this one is going to be to this way. So that's going to be to the right. So this is going to be a positive value because it's going to the right.
Okay.
You got all those EEs and EXPs and that kind of stuff. While you're crunching away at that, I'm going to run to the restroom. Okay?
Okay.
I'm going to waddle to the restroom. I'm so stiff. I should have put it on follow-up.
Yeah, but I'm trying to figure out how does this relate to this? Now I know what the formula is. Yeah, so I knew the formula, but I kept doing like for B to 5.50. I did that for Q1 and Q2. I guess that's why I was getting confused at. But see, he used Q1 is the 3. Q1 is the 2. Oh, now he's not doing this. He actually doing on page 457. He's actually doing on the 7. See, that's Q1. That's Q2. So would this be Q1? Yes. And that's Q2? Yes. Okay. And that's the same.
Y'all get it?
Yes.
What did you get?
So I got 0.928.
0. This is force of A on B. And that's 0.928 125 newtons. Is that right? Okay. That seems fairly reasonable. Okay. But we got to do the other one. Did you already do that one too?
No, I'll wait.
Okay. So the force of C on B is going to be 9.00 times 10 to the 9th Newton meter squared per coulomb squared times 5.50 times 10 to the minus 6 coulombs times, now you don't need to worry about the sign, just write it down the magnitude, 4.60 times 10 to the minus 6 coulombs. Divide that by, now what's the distance between those two? No, wait. You got to get the distance. R squared. Need that. That's 0.750 minus 0.4. That's 0.350 meters squared. Okay? And again, the meter squared cancel out. The C cancel, 2 C's cancel the C squared out. So this will give you newtons here too. And it'll be in the same direction because C is pulling B toward it. Okay? So figure out what that one is. Force of C on B. I would expect a little bit larger number for 2 reasons. At least 1 point something. Did you get? Okay.
At 1.85.
Okay. 1.85.
87.
Okay. And that would,
551.
second?
7551.
551.
Another 7.
Another 7.
Yes,
Okay. And that would be newtons also. So we're going to add these two together because they're in the same direction. 928.125. Add those two together and see what you get. If you still got it on your screen, just add the 0.928125 to it. Okay. And let's see, we only need 3 significant digits because you had 3 there, 3 there, 3 there, 3 there, 3 everywhere. So 1, 2, 3, look to the right. That's greater than 5. So about 2.79 newtons. Is that what they have in the back? I usually have me a piece of paper back there marking the thing.
I usually have a pen or something, so I'll have to keep going back to it.
Number 7. 17.3.
No,
What they get?
for
A part.
A part, they got 0.93 newtons, negative 0.93 newtons.
Wait a minute.
And like the first one, we did get the, it was 0.928, which will round to the 0.93, because it's only 3 digits and the 8 would have rounded 2 up.
Okay, let me read what the question.
You got the negative.
Okay. Now, I didn't do the calculation for it with you, but okay. And you said they got 0.9 something?
For the number 7, part A,
Right?
they got negative 0.93 newtons.
Okay. Number 1, it can't be negative. Okay. This is what? 17.3. Okay. One of the problems is I just don't trust this book. Negative 9.93 newtons. Okay. Now, charge B. Charge B is positive. Charge A is positive. So that's pushing it away. That's pushing it to the right, which should be positive. Okay, and charge C is further to the right, and that's pulling it further to the right. I just do not trust the thing. I don't trust the negative. I don't trust the value. Okay? Now, let's see what 7B does. Okay? That looks like a more reasonable answer. Now, I didn't punch in the numbers, so I don't know, but I trust your calculations, and I am going to put me a piece of paper in the back.
You got 7B.
Okay.
Total force in the original charge A.
Okay. Wait a minute. Oh, wait. I'm in the wrong place. Okay, now I'm in the right place. Okay. On charge A. Okay. Charge B. Okay, blah, blah, blah. Find the total force and direction on charge A. Well, B is pushing A to the left. Would you agree? Okay. So, can I go and erase these others because I don't have room? Okay. So, I'm going to erase. Whoops, I didn't mean to erase that. That will stay the same. That'll stay the same. That'll stay the same. Okay. I'm not going to erase anything there, okay, except this, okay. That's going to be 9, and the force of B on A is going to be the negative of this. So I'm just going to put a minus. Whoa! This drives me nuts. Okay. That's just going to be minus. It's pushing it to the left. Okay? Now the force of C on A, that's pulling it to the right. Okay? So that's the one I'm going to change. Okay? This would be C on A. That part's the same. This part will change. And this part will change. Okay. All right. All right, so let me get my pen back. 9.00 times 10 to the 9th Newton, and then the charge of A is 3.00 times 10 to the minus 6. C is 4.60 times 10 to the minus 6, and the distance between there is 0.750 squared. Okay?
All right.
This one will be slightly that way. Be a pretty small number.
I got 0.2208.
Okay. Let me erase this one. Okay. Force of C on A would be what?
0.2208.
2208. And that would be newtons. Okay? So we have a negative 0.292, negative 0.9281, and a positive 0.2208. So when you do those together, you get a negative 0.7073, which is negative 0.707 newtons.
And the back of these is 707.
Okay, and it should be negative.
And those are got positive.
Okay, then they are wacko, because it's moving to the left. Okay, and then the C. Find the total force and direction on charge C. And I've already erased some things I wish I hadn't. Okay, but the force of A on C, we know that's going to be a minus 0.2208, because see, A is pulling C this way, because they're unlike charges, it's pulling it that way. Mm-hmm. Now we already did, and I erased it, B on C, or we did it for C on B, and if you still have that number somewhere.
So we got the 1.85877.
No, that was the total, wasn't it? Or was that the?
I still got C on B listed on here too, where I wrote it down.
Yeah. And was that what it was?
77.
Okay, I thought it was a smaller number, and that was the number when we added it.
I got 1.85.
Okay. And that's going to be, B is positive, so both of those are pulling it to the left. Mm-hmm. Okay? So we have a negative 0.2208 newtons. And what was the other one? Negative 1.8587. That's enough newtons. And when you add those together, it's negative 2.078, which will be a negative 2.08 newtons. Is that what they got? Okay.
Okay, so
did they put negative on that one too?
That one they put negative.
Well, they got one completely right, one they missed by a sign, and one they wacko. They missed the sign and the number. Okay, but you see how that works?
Okay, so the 0.2208 newtons, and we added the 1.85.
Okay, yeah, well,
okay,
and they're both negative, because you see the A is pulling it because those are like signs, it's pulling the charge toward it, and B is pulling the charge toward it.
Okay.
Now, it's not at all surprising, this is just you see how far A is away from C.
Yes.
So because you're dividing by a pretty big number, that makes it small. Plus, A is a much smaller charge than B.
Yes.
So it has a very small attraction this way. B has a very large attraction because it's a close distance, so it's pulling strongly. And both of those charges are good size, so that's pulling strongly this way. So that's why it's negative 1.85. And both of them are pulling to the left, so that makes it negative 2.08.
Okay.
Now, how in the world they got the other numbers beats me. This one they got the number right, but they had the sign wrong because you see B was pushing A away, C was pulling ever so slightly, and that's how we had a positive this way, but a negative that way, and that gave us that.
Okay. So I know how to do those.
Good deal.
So I'll turn my test in on Thursday.
That's fine.
But I got number 4, number 10 to work out on the test.
Okay. That was helpful? Okay. Yeah.
But is this kind of the same formula that I'm supposed to use for 10? Is that kind of, I was trying to.
Yeah, I mean, those are exactly what we were using.
Okay.
That's the constant, and then that's the charge on A,
Okay.
that's the charge on B, and the distance between those. Now,
I got the distance.
oh yeah, yeah, and that's
Okay.
yeah, and you have to, and you changed it
Yeah,
to
I
meters.
changed
You
it
had
up.
to do that. Yes, absolutely.
Because I wasn't sure at first, but then I was like, well, this has to be
It has to be in meters because
It
that's
has
in
to be
meters.
in
That,
meters.
yeah, there too. So it has to be in meters. Yeah, it looks good.
Okay.
I don't see what that is, but yeah.
I couldn't figure
Yeah.
out which one should I use for the last one.
Okay, this is force of
A and C, I think that was.
C. Okay.
Mm-hmm.
Okay, now, this isn't necessarily A, B, and C. These are just the, if I'm looking at this right, this is the force, this force that you're calculating here
Mm-hmm.
is going to be either the force of A on B or the force of B on A.
Okay.
You know, the only difference is going to be the sign.
Okay.
Okay?
Okay.
Now, don't worry about this sign.
Okay.
That may throw you in a wrong direction or something. What you're interested in is the magnitude of the charges, this, and then you figure out which way it's
Right.
pulling.
Okay.
And since this A is positive and B is negative, A is pulling B toward it, and since A is over here and B is at the origin, it's going to be a positive pull. When you do the other way, charge the force of A on B, did I not say that, or B on A, when you do the other way. Okay, the force is on charge A. Force of B on A is going to be pulling it in the negative direction, and the force of C on A, since it's in the negative direction, and this, so it's going, okay, they're both positive, so they're pushing apart. So the distance is this one plus this one, because one's on one side, one's on the other side. The distance is the total of those added together.
So those two need to be.
Yeah, because 11.5 centimeters this way and -9 that way, you add those two numbers together. So don't let the sign throw you off, because it's how far the total distance is, and then that's divided square. Is that what you're doing down here?
Yeah, that's what I was trying to figure out.
Yeah,
That one right there.
1.753, yeah, okay. And then the thing down here is going to be the sum of those. That's about 20.8, okay? And so that's going to be that. Now, once you have those three calculations done, then figure out which direction you're dealing from. And the one on A, B will be pulling A toward it, so that's going to be pulling it in the negative direction, and C will be pushing A in the positive direction. No. Yeah, pushing A in the positive direction. It's going to be a very small number, though, because they're so far apart. Okay,
Now I
but then
kinda
when
get
you're
it. I
doing on B,
Uh-huh.
then some of the directions reverse.
Okay.
Yeah.
Thank you. Now I kind of see what I was trying to do.
Okay, good deal.
Prior to now, I